Okay, so what we have learned so far, we have your massive signal, intelligent signal, which is called a modulating signal, which is given by VMT is equal to Vm sine 2 pi f FMT, where 2 pi f is your omega, angular frequency. And then we have a carrier signal. Why we need a carrier signal? We have learned that, which is typically a high frequency or unmodulated signal. That is of this form, VCT is equal to VC sine 2 pi FCT. And then we have AM signal, which is a modulated signal. So we have modulating, unmodulated, and modulated signal, which is given as VC plus VM sine 2 pi FMT sine 2 pi FCT. Now, if you see, the frequency part remains the same. It remains sine 2 pi FCT. That means there is no change in carrier in frequency. Your amplitude of the carrier frequency is now changed from VC to VC plus VM sine 2 pi FMT, as shown in expression number 3. Now, that means your amplitude is of the unmodulated carrier is varying in accordance with the massive signal. Okay, the complete massive signal is there in the amplitude part. So only if you see in this expression, only the amplitude has changed from VC to this entire thing in the bracket, VC plus VM sine 2 pi FMT. And then we define the modulation index or the depth of modulation. Why it is important, we'll understand this, which is given by Vm over Vc. That is so it is a factor. It is no unit, but typically it is defined as Ma equal to modulation index into 100%. So obviously the minimum what we can think of 0% and maximum modulation is 100%. What it means? So just to see what it means, let's put in the graphical form the three signals. I move to the next slide. So for that I put it like this. I make it something like this. So this we have what we call time, and here we have amplitude. So we have three signals. So we'll plot all three in one. So we have three signals. Now, in the first signal, we plot it modulating. So let's identify by some graphical form. Okay. Or sometimes we plot it in terms of omega mt also. So that is what you can say, or omega mt. If it is omega mt, that means we are speaking in terms of angular frequency. Then you can have it 0, pi by 2, pi, 3 pi by 2, and so on. So that depends. Normally we put in terms of t, but if you want in terms of the omega mt, so then we can have this one. So I have different signals. Let's talk about this unmodulated signal. So we'll plot the three signals. Let's say we can have it also from here, just for your better understanding. Now we first plot what is called the low frequency signal. Now the low frequency signal looks like this if I put it in a simple form. Okay. So this is one complete cycle up to 2 pi. So your 2 pi, there is one complete cycle. Just put it in a slightly better way. Okay. So that means from here to here, that is a complete cycle. Okay, one complete wavelength starts from here and goes up to 2 pi. Now, so that becomes your what we call the modulating signal, VMT. This we represented in the same color, and that is better. So this becomes your, I am plotting this signal as VMT. Okay. And here, if you see in this range, there is no signal. So it is a low frequency signal. So it is like this. And then we plot in the next one. I use some different color. A carrier signal, VCT, Now, if I plot this VCT, it is a high frequency signal. So that means there is a lot many variations here will be here. So it is changing very rapidly. That means the time period has shortened. So this is your high frequency signal. Why it is high frequency? Because the complete wavelength from, let's say, from here to here is much shorter than the from here to here. So time period is less, so the frequency is high. So this is a carrier frequency plot. Okay. Like in the previous one, this is the one. Okay. And the maximum amplitude here is VM, and the maximum amplitude here is the VC. Okay. So this becomes my maximum amplitude, VM. And here, with the same color, if I use, this becomes my VC, maximum amplitude. So I put it here just to avoid any confusion. Okay. Now, how my carrier wave looks. So how my carrier wave looks, I put it in a different form, which is VAMT. That is the final waveform. So if you see here, how it will look, let me extend this one also, so that now here, if you see, there was no signal, no message was there in the first one, but my carrier frequency is still there. So we will not have any AM wave here, up to from here to here, from here to here. Now here, my AM wave will look like this, which I'm putting in the red color. How it will look? Frequency remains the same. Frequency remains same as the carrier frequency, but amplitude will change in accordance with the amplitude of the message signal. Now, if my message signal is high, so, and this is here, so my message signal will become very high here. Okay. And if you see here, at this point, your carrier wave amplitude is very small. It is very small. So here my amplitude will be minimum. Here it is very small. This is the small, this is the small, no amplitude. That means I will get unmodulated carrier. At this point, I am getting the maximum amplitude of the message signal. So my amplitude of the carrier wave will also be very high. Let's see, but here it is here. So it will become like this. So my AM waveform will look something like this. Here there is nothing is there, no message signal is there. So it will remain the same. Then it will slightly increase, and then it will increase very rapidly, which I'll put this value. And then again, it will be somewhere in middle. And then I will get, let me plot slightly better. But how to get these values, I will explain to you. So you will get an envelope, it is not written very, drawn very carefully, but it is an envelope something like this. So I get an envelope, something like this. Okay. So this is the envelope I'm getting. That means my amplitude of the, this is the envelope. Basically, this is not the waveform, but this is the envelope, which we say. Amplitude of the carrier wave is varied. So frequency remains the same as the carrier. If you see, there was no carrier here, no signal here, but the carrier was there. So my AM wave also will have no signal here. But here my frequency remains the same as the carrier frequency. Okay. So I would say here, in this case, your frequency remains, frequency of AM remains as the same as the frequency of the carrier, because we are not playing with the frequency part. If you see in the last slide, the frequency of the carrier remains the same, FCT. Okay, it is not changing. It remains as the 2 pi FCT here in expression number 2. But if I see the amplitude is changing, and it is changing in accordance with the amplitude of the message signal. So here my message signal has got a very high amplitude. So here also my AM has also got a very high amplitude. Here it is 0. So it is almost 0. I would rather use this thing. It will look like this. So there is nothing. Here also it is nothing. So this point corresponds to this. This point corresponds to this. Again, this point I am getting the maximum one, and so on. So that is my AM waveform will look. If you see, its amplitude is varying. On the y-axis, we have the amplitude. That means my amplitude of the carrier signal is varying. Now, if we have two cases, let's say I have to understand this thing. Let's take different modulation index. So I go to the next slide. Let's say my modulation index, which you have learned, is 1.0. Okay, that means 100% modulation. And if it, what is happens here? In this case, we'll see how my AM waveform looks. So this means how we get M is equal to Vm over Vc. And that means 1 is equal to Vm over Vc. That means your Vm, Vc is equal to Vm in this case. So for such a case, if I plot the three signals very clearly, this is T, this is T, this is T. Okay. Again, I got it like this. So first I plot in the same color. Let's say this is my okay. So this is my Vm. Okay. And again, if I got the high frequency carrier, so this is we plotted Vc, and Vc will look like this. So just to clearly show to you, slightly overlap is there because I had to put in one small board. So this becomes my Vc, and this becomes your same thing, but just more clearly, because in the previous slide I could not make it very clearly. Now in this case, your maximum voltage could be twice of Vc, and minimum voltage could be 0 volt. Okay, so my AM waveform will look like this. So your AM waveform, how it will look. So again, I just for understanding better, I put it in this thing. So this, let's say, is my Vc. Let's say this is my Vm. Okay, so this is Vc, this is Vm. Okay, and in this case, my maximum voltage will be like this. So if I put the AM waveform here like this, it will look I will send you the photographs also from one of the papers. So if you see the envelope look like this. And on this side, so it is like a fish shape. So this looks my envelope, this one. If I take the upper values and the minimum values, not a very good design, but you can refer. So here, basically what I mean to say, this is my V minimum, which is turns out to be 0, 100% modulation. And this is my V maximum, which is nothing. It is twice of VC because it is VC plus VM, and VM is equal to VC. So that becomes like this. So maximum value here we got it twice of VC, and minimum we got it 0 VC, because the depth of modulation is 1, modulation index is 1, so 100% modulation. Now let's change my modulation index to 0.5, 50%. Now if you notice here, it is almost 0. This is 0 here, and here it is just double. So this is the thing to be noted for the, and other places it is increasing and decreasing as per the amplitude of the modulating signal. Now let's take another example. Just I reduce the modulation index by 50%. Let's say my modulation index is 0.5. That is 50%. Okay, 50%. What will happen here? So in this case, it means your VM is equal to VC by 2. Okay, since MA is equal to half, which anyway I've written here. So you're basically, your VM is nothing, it is VC by 2. So if I plot the same things for the different signals here, so this, and this. The first one will take VMT. Oh, sorry, I have to go for this also, just to make it more clear. Let's start with this one. Because VM is, so I will make it very small here. So this is VM, which is in this case equal to VT by 2. Okay. And how my carrier wave will look? Carrier wave will remain the same. That is a double of this VM. So in this case, it will high frequency. So it is changing rapidly. So this becomes your VC, which is nothing. In this case, it turns out to be twice of VM. Okay. Now here, how my carrier wave will look, which I put by the red color, AM wave. So this is the AM signal for MA equal to 0.5. So here my maximum amplitude could be different. It will not be twice. Okay, so it will be slightly different, and minimum will not be 0. So in this case, my AM wave will look like something like this. Again, I put this thing. So this is your VM, which is nothing is equal to VC by 2. Okay, so this is your VC. So it will look like this, your AM waveform. Now here it will not go up to the twice of that, but it will still increase. And at this point, you will not get 0, but there will be some amplitude still there. So something like this. So when you do the experiment, you will clearly understand. So here my envelope will look like this. So this is your envelope, which I'm showing by a darker line. So here, it is not equal to 0. So here, C minimum is not equal to 0. There will be something. And similarly, here my V maximum will not be equal to 1. So what we have seen from this example, we conclude that what we conclude. First is, if I have MA equal to 1, okay, 100% modulation, okay, maximum signal voltage of AM, which is nothing, it is the modulated wave we say, varies between, so that is for your understanding what we have seen in the figure, which we could not draw properly, 0 and twice the maximum amplitude of unmodulated carrier. Okay, between 0 and twice. That is the, we have to understand that. So in the first example, in example number 2, what you have seen, if I have MA equal to 0.5, that means 50% amplitude. So in this case, your maximum signal varies between some minimum value and some maximum value of the unmodulated. So basically, it is not exactly 0 here. It is not exactly maximum twice here. So some minimum, there is some minimum and some maximum value. There is a third thing which we have not discussed, but it is very simple now. If I have MA equal to 0, that means 0% modulation. So in this case, obviously, your original unmodulated carrier signal is the same as modulated AM signal. Why? Because your VM is equal to 0, which means absence of the modulating signal. No, so it remains the same, absence of the modulated signal. Again, how we can understand this? If I see this example, this one. Now here, if you see, there was no signal. In this range, there is no signal. Okay, there is only the carrier. So my waveform will remain just like the carrier itself. It remains the same. So here in this case, it is not modulated at all. Here it is only the original carrier, because there is no modulation here, no message signal. So no modulation takes place and it remains as the original carrier in this particular frequency range, in this particular time period. So this is the third one, which I put it like this. So we could have modulation from 0% to all the way to 100%. Only thing is my amplitude will go on changing. And for the 100% modulation, we see it is between twice and 0 to twice and 0. But every time my amplitude is changing, my frequency remains the same as the frequency of the carrier. Now, sometimes there are cases which we normally see is what we call the overmodulation and splatter. There could be overmodulation case. So what is this overmodulation? So first we'll start with overmodulation, because both are related to one another. So when overmodulation takes place, it actually occurs when your MA is greater than 1, or MA is greater than 100%. So sometimes it happens that your modulation index becomes greater than 100%. So when MA is greater than means, that means your VM is greater than, or VM by VC is greater than 1, which implies that your VM is greater than VC. So if the master signal amplitude is greater than the carrier signal amplitude, overmodulation occurs. See, master signal amplitude is not in my hand. It is something what you are speaking, I can't change. What amplitude you are speaking, it is not. But carrier is in my hand. Carrier, I can choose my amplitude and frequency I want. But it should be higher frequency because I want the lower wavelength and lower antenna size and so on. But I can keep my carrier amplitude smaller than this one. But if my modulating signal amplitude, massive signal amplitude becomes greater than this one, then we'll get the overmodulation. And when you get the overmodulation, it will give you an envelope which is not desirable. It will not give you the actual signal. So basically, what happens? It will result into, so the resulting AM envelope. Envelope we have understood. It just touches the peak point, maximum point, minimum point, and so on, and you get the emblem. Does not resemble your message or modulating signal. It does not represent this thing at all times. Okay. So it cannot be considered as a AM signal. And we should try to avoid it. And how we can avoid it is by making sure that your VC is always less than the VM. And VC is something which is in my hand. I can change the frequency and all those things as AM signal. So we should try to avoid. Then we have what we call the next term is splatter. So we talk about splatter. What is a splatter? So basically, splatter is a some ill effect of the overmodulation. Overmodulation तो हमें पता लग गया क्या हो गया, but उसका disadvantage क्या है? What actually we see and we observe. So I would say it is an effect of overmodulation, and overmodulation is not desirable. So I would say it is the ill effect. Ill means bad effect of the overmodulation. Okay. So basically here it means your one frequency components जो भी हमें मिलेंगे AM wave में, that will fall outside the channel. Let's see this example in our day-to-day life. What it means. जब overmodulation हो जाएगा, so उसका सबसे कुछ bad effect है. What is that bad effect? Now, if you see, there are various radio station, AM radio station, and you tune to one station, second station. FM में जैसे हम लोग करते हैं 98.3, फिर कुछ और frequency, फिर or something like that. So if the overmodulation is there in AM radio, what it means that your signal that is being transmitted over one frequency, it will also go to the other station or other frequency. If you see earlier when we used to listen AM radio, you see your grandfather or grandparents go home and you'll find the old radio. And sometimes when the two stations are broadcasting, let's say one station is broadcasting a cricket commentary, and the next adjacent station is broadcasting something like how to grow vegetables in a field, then what will happen? We used to feel these things because I have also experienced. I was not that young, but yes, I have some weird knowledge that sometimes when we tune this thing, these two signals mix. Sometimes the commentary comes, sometimes the discussion comes on the agriculture, and sometimes it gets mixed. And what we also have seen earlier, the stand-up comedians used to be there. This was their major form of comedy, that they used to mix two stations very well. Let's say one is talking about the commentary and another is talking about the political discussion, and then they mix and match it very well. So this over modulation used to occur very frequently for the AM stations and so on. Now this is about this thing. Now, as we have discussed with our TAs, this Friday your labs will start. So the first lab will be just to give you an introduction to the lab view, which is a typically a software-based lab exercise. Because now we don't have the hardware things with you because you are not physically present. So there is a software which actually gives a feel of the hardware. So the first experiment is basically on the software based lab, which is the lab view. And your TS we have assigned for you will give you that software you can install in your uh, laptops. And when the experiment starts, so just the first experiment which we are going to have this Friday is on the software tool. Then the second experiment will be on AM. And then when you do the AM experiment, we have to find this modulation index. एक सिग्नल हम लोग देंगे मॉडुलेटिंग सिग्नल का, एक सिग्नल हम देंगे कैरियर सिग्नल का, उसका एम्पलीट्यूड डिफाइन करेंगे मॉडुलेटिंग सिग्नल का, कैरियर सिग्नल का एम्पलीट्यूड डिफाइन करेंगे, फ्रीक्वेंसी डिफाइन करेंगे दोनों सिग्नल की, एंड देन विल सी हाउ वी गॉट इट, or we will try to find what is the modulation index and so on. So for the lab purpose, just like we have defined in the theory, that your modulating signal is nothing, it is Vm over Vc. For the lab purpose, we define in a slightly different way. Because if you see this waveform, what we have seen here, we have designed here, it is difficult to find the modulation index from here. You can do the other way around, that you have the modulation index and then you can draw the waveform. So it will look like something like this. But how to actually measure in the lab? So for actually measuring in the lab, we find the index in the lab. So this is basically this signal give uh,
Sir, your voice is not clear.
Yes, sir, your voice is breaking.
we got develop. We can develop the carrier signal from two different emitters, and then let's amplitude. So in this case, how to go for this? So what is given us? We, as I said, the maximum could be here.
Excuse me, sir.
Yes, yes. 1 minute, 1 minute.
Sir, your voice is not clear.
Yes, yes. Just wait. A minute. Let's. Here. Okay. Now you can listen me properly. Am I audible properly now?
Yes, sir.
Okay. So for that point of view, we have to slightly understand the modulation index, how to measure that in a different. What we have seen is the V maximum of wave is given as Vc plus Vm. So this is my what we call the V maximum, which is said is given as Vc plus Vm. Like for 30% modulation, it is twice of Vc by Vm. And then we have minimum, which is 0, which is I define as Vc minus Vm. So my Vc over, I can write down this expression as Vc 1 plus Vm over T, which is 1 plus V. So I'm trying to work out MA value in terms of the VC. Can you see my on the board? Which is yes or no?
Sir, voice is still breaking.
Yes, sir.
But can you see my what I'm writing? Now it is okay.
Now it
What
is.
I am now it has come. Right? Really, I can do the V minimum as VC minus Vm. What understanding we have got? There is in what I'm writing and what I'm saying I is delay there. And is that Vm over VC, which I could write down VC 1 minus no, this is value 2. It is given as 1 plus M over. This is for the
Sir,
that is
voice is still breaking.
yes.
Not clear.
Uh, uh, for the the speed, I could see delay. What I'm writing and what you're seeing is there is some delay is there, and because of that there is a thing. So let me do. So can I end the call and again start the call? But that will take long time. So just please listen to me carefully. I am trying to go a bit slow. Okay. So can you see my whiteboard? What I'm writing?
Yes, sir.
One
Yes, sir.
Can you see my whiteboard?
No, sir.
No? 1 minute. 1 minute. 1 minute. Then just wait, please. I will call some help, some technical help. Let me see. Is my whiteboard visible now with some arbitrary waveform? Hello?
No, sir.
No?
No,
No,
sir.
sir.
No.
Some things I have put there. Arbitrary drawing. No. Just wait, please. Then. Is it visible now?
Yes, sir.
Yes, sir.
With some arbitrary drawings. Huh? Hello?
Yes, sir.
Yes, sir.
Okay, fine. Then I will start now. 1 minute. Okay. Is it now visible? Once again, I am confirming before I start.
Yes, sir.
Okay. So what I was saying, I could not trace out the problem. I just rejoined. So for the measurement of the modulation index, which will be your lab part, lab number 2, we slightly put modulation, we measure modulation index in a different form. Now, if you see here, we can define Vmax as Vc plus Vm, which I can rewrite as Vc1 plus Ma, because the maximum amplitude 100% could be like Vc plus Vm and twice of Vc when Vm is equal to Vc, and the minimum will be given by this one. And for 100% modulation, V minimum is 0. That means your modulation index is 0, so your V minimum is exactly as the carrier wave. So if I take the ratio of V max over V minimum, it is given by this one, and I can find out in terms of this equation. Now I'll remove this slide. Okay. So what we got it. So from here, what we got is something. If I go to the previous slide, what was that? Yes, V maximum is given by this one, V maximum over V minimum. So just solve this equation. So it becomes a 1 minus Ma V max is equal to 1 plus Ma V minimum. Or I could write down this as V maximum minus Ma V maximum is equal to V minimum plus Ma V minimum, which means I could write down by Ma, or let me put one more step for you. So I could write down this as V maximum minus V minimum is equal to V maximum plus V minimum Ma. I brought the Ma terms on one side, and which gives me my modulation index as V maximum Y minus V minimum over V maximum plus V minimum. So that is how we normally use in the lab to measure this modulation index. Because as I told you, in my lab, we give one signal, which is my modulating signal, and we give the carrier signal, which is of higher frequency and some amplitude, and then we get something like a waveform like this. Now, using this waveform, we find out what is my V maximum and V minimum, and just to use this formula to give you the modulation index. So obviously, in the case of 100% modulation, it is very clear that I will get V maximum as twice of Vc and V minimum as 0. Okay. So this is how we see it from the lab point of view. Now let's see the frequency representation of AM signal, which is a new topic. So to go for that, and this. Now, coming to the new topic, which is what we call the frequency domain analysis. So far, we have done in the time domain. That means on the x-axis, we have time, and the y-axis, we have the amplitude. That is what we do in the normal lab, like in oscilloscope. Your x-axis is time. Frequency domain means how my signal is changing with respect to the frequency. So of the AM signal, what frequencies I will get. Now, if you recall, we know the AM signal is given by as VAMT. Now we know, we could write down this very clearly as VCT 1 plus, sorry. 2 pi FMT sine 2 pi FCT. So that is something which we have learned. I could write down in the form of modulation index also, which we can rewrite as VAMT equal to VC. I take as common. And we can write in the form of modulation index also. How to go for that? I want to bring the modulation index in this one. So I could write down as VC. I take it common. 1 plus VM over VC sine 2 pi FMT sine 2 pi FCT. Which also I could write down this as VC 1 plus MA. Because this is nothing. It is your modulation index sine 2 pi FMT sine 2 pi FCT. So this is another form of the AM in the form of using this modulation index. Earlier we used to write in the form of separately like this, but now there is no VM, no VC, but in the form of MA. So this is your, I would say, the general expression of AM signal. In terms of modulation index, which is MA. So that is the new expression I got it, which is the number 4. Number 1 was for this, number 2 for carrier, number 3 for this amplitude modulation using this for number 3, and this is number 4. So these two expressions, now we'll use this expression quite often in terms of modulation index, because it also gives me the depth of modulation, everything. I can see how my picture will look. So coming back to this one, frequency domain. So I got this expression number 4, something right, this thing, okay, which I got it here. And further solving this, it gives me something like this, VAMT, nothing great, very simple things I am writing for you. It gives me VC sine 2 pi FCT. That is the first term we got it. If you see this expression, first term becomes VC sine 2 pi FCT, okay, 1. And the second term becomes MA VC sine 2 pi FMT just to make it clear, sine 2 pi FCT. Okay, nothing great. If you see here, that is my first term, VC sine 2 pi FCT. The second term becomes VC MA sine 2 pi FMT, and that means this product of two sine function is the second this thing. Okay, product of two sine function, this and this. So if I go here, it becomes like this. Now, if you see here, the first term exit is the carrier signal. This is nothing. What we have seen here is your first term is nothing. Is carrier signal. Okay. And the second term on RHS is product of two signals. What are those signals? One is the modulating and carrier signal. Okay, that is very clear. So what we do here, I use, now we know sine A, sine B. So here also we use that identity, sine A, sine B. This is like two functions of sine. I know that it is given as half cos A minus B minus cos A plus B. You can assume sine and cos in the first expressions only, as I said, but it need to be sinusoidal. So if I use this identity, I rewrite this expression as VAMT. First term remains the same, which is my carrier frequency, sine 2 pi FCT. But the second term will now split into two terms. So it will become plus MA by 2 MA VC by 2. That becomes amplitude cos 2 pi FC minus FMT. I put FC first because FC is, so this becomes my A part, this becomes my B part in the trigonometric person. So I put FC minus FM because FC is normally higher frequency. So it becomes FC minus FMT. That is the first part. And then we'll have another expression because of this trigonometric identity, VC by 2 cos 2 pi FC plus FMT. So my expression for AM now becomes something like this in the frequency domain. That means I have three frequencies. One is the original carrier frequency, the first term. Then we have the sum of the two frequencies, the message signal and the carrier frequencies. This is the second term. And the third term is the difference of the two frequencies. So this is my expression, what we call in the frequency domain. So I highlight this thing. The previous one, what we have here, that was in time domain. Okay. But now I could see there are three pictures, three frequencies I'm getting in this figure. So this is the AM signal in frequency domain. That means I will have in my output, when I send my message signal over a carrier, three signals. One is the original carrier frequency, the first term. So this is my equation number 5. Now I can say this is the 5. Then we have another one, which is given as difference of the two frequencies and the sum of the two frequencies. So these are the three frequencies. Obviously, the amplitude will be different. Carrier has got the same amplitude as VC, but my sum and difference of the two frequencies will get the amplitude as MA VC by 2. So it depends upon the. Now here we have got two frequencies, as I said, two extra frequencies. So which I highlight using this one, this one, and this was my original. So let me see what I could write out here. So I get first term, just one minute. First term is your carrier signal, unmodulated. 1 minute, let me finish this, then you can ask. Carrier. which is FC. Second term is FC minus FM. And third term is FC plus FM. So this is what we call the lower side frequency. And this we call the upper side frequency. So I have three frequencies in my AM signal. If I see the frequency domain, F here, so there is a carrier frequency, and there is something what we call FC plus FM, and there is something what we call FC minus FM. So this is called the lower side frequency. This is called the upper side frequency, USF. So basically, my information, which was my message signal, will be contained in all the three frequencies, okay, because that is my amplitude modulated wave. It is also contained in the carrier. It is also contained in the two-side wave. Their amplitudes are nearly the same, so I'm putting it like that, but this has got a different amplitude, which is the original carrier amplitude, okay. And this amplitude of the sidebands depends upon the modulation index. Yes, somebody was asking some question. Let me try to answer right now, if it is possible. Yes. Yes, your question, please. Someone was asking a question. Anyway, I could not recall. So this is how we get the frequency spectrum. And that is my expression for this AM signal, how we got it. So obviously, in this case, your amplitude wise, if I write, so this has got the amplitude of VC, which is nothing the amplitude of the carrier. But this is what we call V upper sideband, V lower side frequency, upper side frequency, and lower side frequency. Or sometimes we use the word lower sideband or upper sideband, okay, when it is a band of frequencies. So in this case, your V lower side frequency is equal to V upper side frequency, which is given as MA VC by 2. So this is the amplitude of the two frequencies, the sideband frequencies, which have the same amplitude. So my information is contained not only in the carrier, which I used for transmitting, and in the process we generate two frequencies. One is the lower and upper, and their amplitudes are given by this one. Okay, just to take one example of this frequency representation of AM signal. So as I said, I always follow with some example. So example is something like this. Let your carrier frequency, which is a higher frequency, is 1 megahertz. Your modulation frequency is, which is a lower frequency, is 1 kilohertz. Okay, which normally we convert everything into megahertz or kilohertz. So either you convert, because both frequencies are different. So when you solve the problem, either convert into megahertz or into kilohertz, but it has to be the same this thing. Now, if we have this one, and let's say I give the amplitude also, and let your VC is 1 volt, okay, and modulation index I measured as 0.5, okay, which is a 50% modulation. That is the 50% modulation. So in this case, what we solve it, how we solve this problem, okay, let's see. So if I see this data, carrier amplitude is 1 volt, okay, V of lower side frequency is how much? Given as MA VC by 2. So it turns out to be 0.5 into 1 by 2. Okay. So it turns out to be 0.25 volt. And this is also the upper side frequency is also same. So it also turns out to be 0.25 volt. And carrier amplitude turns out to be 1 volt. And I will get two frequencies. That was from the voltage point of view. FC was 1 megahertz. And then we have lower side frequency, which is given as FC plus minus FM. That means it will be 1 megahertz. See how I solve this problem? Minus 1 kilohertz. They are different frequencies. So I can retain it in terms of megahertz. So it becomes 0.999 megahertz. Okay. Because this is nothing. It is equal to 0.9001 megahertz. Okay. And your upper side frequency turns out to be FC plus FM. So in this case, it turns out to be 1 megahertz plus 1 kilohertz. And it turns out to be 1.001 megahertz. So when I transmit a carrier frequency of 1 megahertz and modulating frequency of 1 kilohertz with the amplitude 1 volt and modulation index I have given, so I could find out from this the three voltages of the three frequencies and the three frequencies. One was the original carrier. So my AM signal will get three frequencies, 1 megahertz, 0.999 megahertz, and 1.001 megahertz. And with the amplitude of 1 volt, 0.25 volt, 0.25 volt, respectively. So for this case, I could write my expression for AM wave as by using this equation, which we got it something like this. So what I mentioned is equation number 5. Okay, if I see this equation number 5, I could write my expression for AM. And therefore, my AM wave will look like this. V AMT is equal to VC is 1. So it will be simply 1. So 1 sine 2 pi into 10 to power 60. When we write this expression, we always write in terms of megahertz. So 10 to power 6 hertz only. So this becomes this one. And then in this case, my amplitude turns out to be 0.25 cos 2 pi 0.999 into 10 to power 60. And plus, I will go to the next slide, which turns out to be plus, oh, sorry, it will be a minus now because this is the third expression is minus. So it becomes minus 0.25 cos 2 pi 1.001 into 10 to power 60. So I got three frequencies. Forgive me, because part of the expression in the previous one. One is the original carrier, which has got amplitude of 1 and sine 2 pi into 1060. And here the two frequencies with the amplitude 0.25, 0.25 and all those things. So how my AM waveform signal will look in the frequency domain, if I plot this thing in the frequency, it will look like this. So frequency spectrum will look like this. So I have got one frequency as 1.000 megahertz, which is my FC. I got another frequency which is 1.001 megahertz, which is nothing, it is FC plus FM. And I have another one which is 1.999 megahertz, which is FC minus FM. So this is my frequency spectrum. So this is my frequency domain or spectrum of AM signal. So it is with respect to the frequency. Previously, we used to see, if you see, on the my x-axis used to be the time or omega mt, 0 to pi. And the amplitude, so I will have another frequency here. And their amplitude, if I see here, turns out to be, if I see the amplitude wise, it is 0.25 volt. And here it is 1.0 volt for the carrier. So the two, my information is contained in three frequencies, the lower side frequency, upper side frequency, and they have got the different amplitude. Sometimes when we transmit a original signal, like my speech, it has got one frequency, let's say, one proper sinusoidal, FM. But sometimes, as I said, in an orchestra, we transmit many frequencies simultaneously. That my message signal will have many frequencies. As I told you, one could be tabla, one could be orchestra, one could be flute, one could be harmonium, and a single carrier. So one frequency is getting transmitted, and let's say at last time in this example, if I have taken 1 kilohertz, another will be 0.99 kilohertz, another will be 0.7 kilohertz, 0.8 kilohertz, 0.9 kilohertz, 1 kilohertz, 1.2 kilohertz, which I want to simultaneously transmit. And I simultaneously transmit over one carrier, okay, which is of 1 megahertz. So I will get various signals now, which could be 1 megahertz plus 0.7 kilohertz, 1 megahertz plus 0.8 kilohertz, 1 megahertz plus 0.9 kilohertz. Then we use the word band. So it is a band of frequency, upper sideband, lower sideband. So in that case, it could be something like this. My spectrum will look like this. So my carrier frequency remains the same as FC, okay, of amplitude, which is VC. And then I have a upper sideband and I have a lower sideband. So this becomes my, what we called upper sideband. So if my message signal consists of various frequencies, let's say in orchestra, so we use this word upper sideband, USB, and the lower sideband. But a single carrier. So obviously my modulated signal will have various frequencies. So here I could have FC minus FM maximum value of FM. And here I get FC plus FM, but the maximum value of the FM signal. Okay, and this is FC. So this, if I plot frequency versus amplitude for a band of frequencies, as I said, it could be 0.7, 0.8, 0.9, 1.2, 1.3, 1.4. So my original carrier is 1, and it becomes 1 minus 0.7 here, and 1 plus 1.2 on the other side. So in that case, we get the band frequencies. So if you see from this expression, my bandwidth of the AM signal will become slightly different. So let's understand this. Let me see what is the time. So we'll talk about what we call the next class. We'll talk about AM signal bandwidth. Because now I got this thing. So what is the bandwidth of my AM signal? So that we have to understand in the next lecture. Sorry for disturbance of 10 minutes in my this thing. Any queries? Somebody was asking some question. I don't want to leave him just like that. Any question? Yes, you could ask any arbitrary question also. Sometimes they are very interesting to answer, and I always prefer. But yes, you should be open to questions. So I will share this slide, I think, in a week or so. Nothing to worry about. I don't know why I'm not getting the list. Have your sections have been defined? You already
Yes,
got the list?
sir. Means most of the students are already fixed,
Okay.
right? So
Okay.
due
Okay.
to like
हिंदी में
sir,
बात
just
करो.
changes of 2 or
हम्म,
3 students, like it is not
Okay.
needed
So
to.
what is the first ID number of section B, which I'm teaching? Any idea? It starts from 190 or 170 or something like that.
Sir, 171.
171. Okay. So I will form a group and I will share the slides. Okay. Any other question? Any other query? Okay, fine. So this week there will be lab also, which will be a introductory software lab, which is like you get a feel of hardware. And the next experiment will be on AM. And we'll comfortably finish my AM part, which is also useful for the lab, by this week. So you'll be much easier in handling that second lab also, which will be next Friday. So I stop it here, share the slides with you, and sorry for that small disturbance which we normally encounter in such lectures. Okay, fine.
Hello, sir.
Yes, please go ahead.
Can you go to the 10th page?
I go to the 10th page. Yes, 1 minute. 13, 12. Yes.
Here, sir, in before the third term, it should be minus.
Before the
Third.
fine. But yes, sir. Oh, thank you. Very nice. Correct. Because that is the okay.
Okay, sir.
Fine. Thank you. But in the problem, when I just solved it, I took it minus, if you got. Okay.
Yeah.
Fine. Yes. Okay. Thank you for that. Okay. So I just leave it here and I will share the slide. It is 171 onwards. Huh? Okay. Fine.